Okay, welcome back. When we left off last time, I had asked you to answer these questions on your own. So we're going to go over them. What is a force? The definition of a force is a push or a pull that one body applies to another. Now remember, in physics, when it says one body, it's not like a dog's body or your body or my body. It's any object. Combination of all the forces on an object is called net force, which is the sum of all the forces acting on an object, or as we say in physics, the body. What are balance forces? Balance forces are equal in size and opposite in direction. Because they're equal in size and opposite direction, they cancel out and their net force is zero. So since their net force is zero, zero force means exactly what it says. There's zero force, and because there is no force acting on an object, the total is zero, then its motion doesn't change. So if it's at rest and it's not moving and there's zero total force acting on it, it's going to stay there. And if it's moving and the total force is zero, it's not going to change the way it's moving. Okay, draw the three examples of the balance forces we had in the notes. Balance forces, okay. We got this block, okay. One example is there's just one force acting in a direction, it's 15 newtons to the left. Okay, these forces are unequal in size and they're in the same direction. They add together for a net force of 45 left. They could be unequal in size and in opposite directions. So we got 15 pushing this way, 40 pushing that way. We have a net of 25 pushing to the left. What is gravity? Gravity is a force of attraction between any two objects. So everything that is an object has mass. So all objects have a force of attraction between them. Okay, but it depends on the amount of mass and weight. So most things, because their mass is so small compared to the Earth, their force of attraction is tiny. Okay, weight, when we talk about our weight, is a measurement of gravity's pull and is measured in the SI system. It's measured in newtons, which is the abbreviation is N. Or in the standard system, we say our weight is in pounds. The two things that gravity depends on are mass and distance. So the greater the mass of the object, like the Earth versus the moon, the more gravity the object has. Also, the farther you are away from the object, the farther you get away from the Earth in the space shuttle, things appear to float because there's a long distance from the Earth. So in an airplane, your weight would decrease because you're a farther distance from the Earth, but your mass would stay the same. So you wouldn't change size, okay? It's not a way to lose weight and change size quickly, you know, going in an airplane. In this next section, we're going to learn a little bit about friction. Okay. Friction sounds something like gravity, okay, because it's between any two surfaces, okay, whereas gravity was between any two objects. The key here, it says it's between any two surfaces that are touching each other, okay? So if they're not touching, there's not going to be friction between them, okay? So anytime surfaces are touching, there's friction. Micro welds are what cause the friction. So if we had a super magnifying glass and we looked at even the smoothest surface, like the glass on a mirror or something that we thought was highly polished, okay, it would look like this, like kind of like sandpaper and be all craggly, okay, and it would stick together. So you can see how these things stick together, and when you try and slide them, this is where the friction comes from. So I put in your notes that no surface is perfectly flat. There's these tiny micro welds on everything. These bumps lock together like sandpaper and trying to stop the motion by gripping each other. Micro welds oppose the motion, okay? So if you're pushing on the top one to the left, it's going to oppose that and make it not want to move to the left. You know, there's different types of friction, and most of them are kind of pretty obvious, okay? First kind is when the surfaces are not moving, and two surfaces that are not moving is called static friction. Okay, it's like static electricity is electricity that's not moving. So that literally that's what the word static means, not moving. So this is not moving friction. It says between two surfaces that are not moving. So like your book sitting on a desk, that's static friction. The reason why the book doesn't just start sliding around is because the two surfaces are touching. Okay? And then friction will hold the book in place or the object in place until an unbalanced force acts upon it. So contrary to what kids often try and convince teachers is that things go flying through the air in the classroom on their own. We know that that's not true. Okay, things don't just move on their own. An unbalanced force has to be applied to it. Now, if you push on the book and it begins to slide across the desk, that kind of friction is called sliding friction. Now, we're going to take a look at this little video segment and take a look at some of the different kinds of friction. Okay, this is a little clip on friction. I'm going to point out a few things as the video plays.
Friction is the force that slows things down. Friction occurs when two objects rub together or try to slide past each other. If you rub your hands together quickly, you will find that within seconds your palms become warm. One of the products of friction is heat. The friction between your palms produces heat. Next time you go for a ride in the car or on your bike, feel the tires after you've stopped. The heat you feel is from friction.
Okay, so the first kind of friction when he was rubbing his hands together was sliding friction. Now we're looking at an example of rolling friction.
Produced from the car's brakes rubbing against the tires. Look at the soles of your shoes. You should discover that they're worn down. Where once new, clean treads existed, you probably have worn surfaces.
There are two products of friction, heat and wear. So in the first example, when the kid was rubbing his hands together or when they had the rolling friction on the road and the tires got hot, that's an example of heat. And then the wear, like on your shoes or tires wearing out.
So another effect of friction is to wear things down. The friction between your shoes and the surfaces on which you walk and run has affected your soles. Look at car and bike tires, and you'll also see evidence of wear and tear brought on by friction. So, friction slows down an object until it stops, produces heat, and wears the object down. To avoid the wear and tear of friction on cars, we use lubricants, such as engine oil, to make the engine surfaces slide easily past each other and cut down on heat. If we didn't have friction, things would be very crazy.
Now remember, in inertia, an object in motion would stay in motion or an object at rest would stay at rest. So they're going to try and give us some examples of how we said that friction slows things down and opposes motion, and without it, they would just keep moving forever, or there would be no friction for us to get moving. So our shoes wouldn't stick to the ground.
For instance, the process of walking or running occurs because of friction between our feet and the ground. Without friction, a person at rest or at a standstill could not get moving. And objects that were moving would not be able to stop because they require friction between their surface and the ground to slow down. Here is a computer game for playing billiards. We can turn the friction level to a setting that is very close to zero. Watch what happens when the cue ball is hit into the other balls. All this motion and uncontrolled activity is a result of very little friction. The inertia of the balls keeps them moving in straight paths until they strike other balls or the sides of the pool table.
Fluid friction is sliding friction in a fluid. A fluid is anything that pours or changes shape easily. So like a liquid or a gas is considered a fluid. So when something slides through the air, that's fluid friction. When something slides through water, that's fluid friction. So like when a space capsule comes through the atmosphere, that's fluid friction because it's sliding through the air. When a bow of a ship goes through the water, that's fluid friction. So it's important to remember a fluid is a liquid or a gas. Okay, so I put in here like a boat's bow sliding in the water. Okay, this is a picture of the one of the Apollo capsules. And when it left Earth, the bottom of this was white. It had something called a heat shield on it. And when it came through the atmosphere, the air sliding against it, okay, was that sliding friction. But when it slides through a fluid, it's not like two solid surfaces rubbing together, okay? It's the solid space capsule rubbing against the fluid, which is the air. But because there's friction, friction produces heat and wear. You can see how the bottom of the capsule is worn now, okay? And it also got burned, okay? So there's evidence of heat and wear. Okay? This is a picture of the ship moving through the water, okay? And actually there's two fluids here. The ship is moving through the air, which is a fluid up here, and then it's moving through the water, which is a fluid down here. So as the water pushes past the ship, there's fluid friction. And also it needs power from the sails to push itself through the air, because the air resistance would also make it want to stop, which is a type of fluid friction. We're going to take a look at this little video clip, and they're going to show us some other examples of fluid friction. Okay, in this second little clip, we're going to take a look at fluid friction.
Contact between solid objects, but it also applies to things that aren't solid, and this is called fluid friction. I can't think of a more fun way to show it than in the sport of water skiing. We know water is a fluid, but actually, so is air. A fluid is any substance that can change shape very easily and move around other objects. Fluid friction is the force opposing the motion of fluid over an object.
Look at as the ship goes through the water, the fluid is sliding past the hull of the boat.
Remember my car wash? Spraying the car with water produces friction between the car, the dirt, and the water. Obviously, to go water skiing, you have to start in the water. The fluid is all around you, and there's a lot of friction against your body and the water ski. The key to water skiing is to reduce the friction enough so you can move fast. That's where the water ski comes in. It's made so that the water slides easily over the ski. When a skier is pulled by a powerful boat, the pull of the boat lifts him out of the water and he's off on a wild ride. By shifting his weight on the ski, he can control the amount and direction of the friction to make turns. And the water isn't only making contact with the ski. There's obviously fluid friction happening as the boat pushes through the water, too. The only reason the boat and the skier can keep moving is because the force of the boat's engine is stronger than the force of the friction. If the engine were to quit, the fluid friction would immediately start to slow them both down until they stop moving.
Next kind of friction is rolling friction. And in the first video clip, we saw some examples of rolling friction. Rolling friction is when an object and a surface touching it. So like car tires on the road. Okay. Now, air resistance is one of the special kinds of fluid friction. So we kind of have taken a look at that. Okay, with the space capsule. As the space capsule came falling to the atmosphere, there was the air resistance, the fluid friction of the air pushing on them. Now, and it says it's a force that opposes gravity. Okay, as it was falling, the air was rubbing and slowing the space capsule down. Okay. So it depends on a couple of things. It depends, the amount of this fluid friction, the amount of the air resistance depends on the object's shape, the size of the object, and the speed at which it's falling. Okay. So over here, I drew some pictures. Okay. Before you let something go, it's just sitting there and there's no air resistance. When you first drop it, it's moving slowly. So there's only a tiny amount of air resistance underneath it. As it falls faster and faster, the air resistance builds up. Okay. Now, in these three diagrams, the force pushing down is gravity. So gravity is the same on the object, no matter whether you're just holding it in the air, whether you just let it go, or it's been falling for a while. So this gravity arrow, this force is the same. as it's falling slowly, the amount of air resistance is small. So it continues to fall faster and faster because we have unbalanced forces here. The force pulling down is greater than the force of the air resistance pushing up. Eventually, at some time, it's going so fast that the amount of air resistance is equal to the force of gravity. Now, this doesn't mean that it's going to stop and float. Balanced forces don't change motion. The motion of this thing was falling. So it was falling at some speed. It's just not going to change speed anymore. It's going to continue to fall, but now it will fall at a constant speed because the forces are balanced. Over here, I showed that if there was no gravity, if there was no air resistance, only the force of gravity would be acting on the object, and there would be nothing pushing underneath of it to slow down. So it would just continue to fall faster and faster. Okay, so I put over here what we just said. Remember, the gravity pulls the same on everything with the same force. So the force of gravity in these pictures doesn't change. The reasons things fall faster or slower is that air resistance opposes motion and slows them down at different rates. If there was no air resistance, no atmosphere, things would fall at a constantly increasing speed, and they would all fall at the same rate because there'd be nothing to slow them down. They showed us this on one of the Apollo missions. They brought a hammer. They brought a hammer and a feather to the moon. So in this example, we'll see that they fall at the same rate because there's the same amount of gravity pulling on both of them. In the absence of the friction from the air, objects would fall at the same speed because only the gravity of the moon is pulling them towards the moon.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
Let's take a look at that one more time.
They'll hit the ground at the same time.
Okay, so he's going to drop the hammer, and then he's going to drop the feather. There's no atmosphere on the moon, so there's no air resistance. So there's only the downward force of gravity pulling on both the hammer and the feather. And they hit at the same time.
That proves that Mr. Galileo was correct in his findings.
In this last clip, we're going to look at some skydivers and see how when they first jump out of the plane, they fall faster and faster and faster. Gravity continues to pull on them the same, but the air resistance underneath them builds up until they fall at a constant speed. Okay, now in this next little clip, we're going to take a look at gravity and terminal velocity as these skydivers jump out of this airplane.
Now, if you consider that objects speed up as they fall, that means that something falling from a great height, like, say, a skydiver, would just keep falling faster and faster. But here...
Now, that would be true if it was like the Apollo on the moon, where he dropped the hammer and the feather and there was no air resistance. If there was no air resistance, then gravity would just keep pulling them down to the earth and they would continue to accelerate faster and faster. But we said, as an object falls, one of the things that happens is the amount of air resistance under the object builds up until the force pushing up is equal to the force pushing down. When that happens, okay, it doesn't make the person stop. The forces become balanced. Balanced forces do not cause a change in motion, so the person's motion continues. They continue to fall, but they don't accelerate anymore because now the forces are balanced, so they fall at a constant speed.
Here's where air resistance comes in again. The faster an object falls, The more air resistance builds up, slowing it down. The force of air resistance fights against the force of gravity. Eventually, the two forces balance out and the object stops accelerating, speeding up. This is called terminal velocity. The object keeps falling, but it doesn't speed up anymore. It is now falling at a constant rate.
We're going to pick up here next time. I'd like you to answer these questions on your own.